day, Mamich. I'm Andrei Jyuan Maningas from 11th STEM A.
And I'm Karl Tabo, also from 11th STEM A.
And in this video, we will discuss about the fundamental trigonometric identity.
So the fundamental trigonometric identities are the reciprocal identities, quotient identities, Pythagorean identities, and the even and odd identities. Before we dig into those identities, let us first recall the values of the trigonometric functions with the corresponding theta inside the unit circle, where sine is equal to y, cos is equal to x, tan is equal to y over x, cosecant is equal to r over y, secant is equal to r over x, and cotangent is equal to x over y. So why do we need to recall these values? It is because these values are very significant to understand the identities we will talk about later.
Thank you, Karl. Now it is the perfect time for us to tackle about the fundamental identities because we already know the values of trigonometric functions inside the unit circle. So now the first set of the fundamental trigonometries are the reciprocal identities and the quotient identities. So we can see from the definitions that Karl gave us that these identities follow from the values, and we can take note that these identities hold if is taken either as a real number or as an angle. So now let us start with the reciprocal identities. So the reciprocal identities are the reciprocal of the six main trigonometric functions, namely sine, cosine, tangent, cotangent, secant, and cosecant. The important thing to note is that the reciprocal identities are not the same as invert trigonometric functions. Every fundamental trigonometric functions is a reciprocal of another trigonometric function. For example, cosecant is the reciprocal identity of the sine function. So we can see from the presentation that cosecant theta is equal to 1 over sine theta. So and we can see also there that there is secant theta is equal to 1 over cosine theta, and cotangent theta is equal to 1 over tangent theta. So this means that if cosecant theta is equal to 1 over sine theta is also equal to 1 over cosecant theta.
Now the next one is quotient identity. The quotient identity is an identity relating the tangent of an angle to the sine of the angle divided by cosine of the angle. This is basically a simple substitution on the values of circular function. For us, we know that tan is equal to y over x. If we substitute it, it's just gonna be sine over cosine because y is equal to sine and x is equal to cosine. And the same goes for the cotangent.
So that will be all for the first set of identities. Now it is the time for the next one, which is the Pythagorean identities. In the word itself, we can have an idea where these identities came from. And if you are thinking about the Pythagorean theorem, you are right. To better understand these identities, let's have the first one, which is the identity one, which is the sine squared theta plus cosine squared theta is equal to 1. Remember the Pythagorean theorem, a squared plus b squared is equal to c squared. It looks familiar, or it looks similar to this identity. But how? Remember, when we put the triangle or the Pythagorean triangle inside the unit circle or inside the circle, the values of the A, B, and C change. A will be equal to x, and B will be equal to y, and C will be equal to r. But we know that the r inside the unit circle is 1, or the radius, and r squared will be also 1. So therefore we get the standard form of the unit circle, which is the x squared plus y squared is equal to 1. But wait, there's more. We all know that also in the unit circle x is equal to cosine y is equal to sine, and r is equal to 1. Therefore, we get the Pythagorean identity number 1, sine squared theta plus cosine squared theta is equal to 1.
As for the third identity, we can get it by dividing all the terms by cosine. So sine divided by cosine, again, going back to the quotient identities, it is equal to tangent. Then cosine over cosine is just equal to 1. Then 1 over cosine, going back to the reciprocal identities, it is just equal to secant. Therefore, our third identity is tangent plus 1 is equal to secant. Again, like the second identity, we can also derive other identities by using APE, which is... And here is the visualization of the third identity. For the second Pythagorean identity, we can get it by dividing all the terms by sine. So sine divided by sine is just 1, and cosine over sine, going back to the quotient identities, it is equal to cotangent. And 1 over sine, going back to the reciprocal identities, it is equal to cosecant. Hence, our second identity is equal to 1 plus cotangent is equal to cosecant. And from here, we can derive other identities by using APE, which is... And here is the visualization of the second identity.
So thank you again, Karl, for that wonderful explanation about the Pythagorean identity number 2 and number 3. So now let's go to the next set of identities, which are the even and odd identities. So what is this even odd identities? Before we tackle about it, let us first recall what are the rules of function when it comes to even and odd functions. So an even function said to be the f of negative x is equal to f of x, and the odd function is equal to f of negative x is equal to negative f of x. And that's how we get this even and odd identities that is present in our presentation. We can see that cos of negative x is equal to cos x, and we can remember that cosine is equal to 1 over secant. So that's why cosine and secant are both even functions, because they are similar, or they have the same sign. And the odd functions are sine, cosecant, tangent, and cotangent. To really understand how these even and odd identities work, or how we arrive for this even and odd identities, let us first recall about three main topics that we already tackled about in the past lesson. So the first will be the graph. We can see in each graph that, or we can see in the graph that there is something to do with these even functions, and we will know it later, but just recall to better understand. Next is the quadrant rules, and third is the coordinate and coterminal angles. So now let's have an example. So we have here the sine negative theta is equal to negative sine theta. To prove this point, let's have an example. So there we can see, let's have an example which is the sine negative pi over 2. So we all know that in the coterminal angles, negative pi over 2 is also equal to 3. Wait a minute. Let's see here that it is equal also in the 3 pi over 2. So that lies in the third between the third and the fourth quadrant. So that will be negative sine, because y, sine is equal to y. So we can see here that we encircle the sine negative pi over 2 in the graph. So in the graph, like I said earlier, we can see how these identities work. So the sine negative pi over 2 is also equal to sine 3 pi over 2. So that will be negative 1, because it is 0, negative 1, the point of the 3 pi over 2. And we said earlier that sine negative theta is equal to negative sine theta. Therefore, if sine negative theta is equal to negative 1 and sine theta is equal to 1. Therefore, negative times positive 1 is equal to negative 1.